prizes, sign my name, publish and perish all the same.
We're going to continue this morning to penetrate into the modeling world and the numerical world. And so if you remember, yesterday, we kind of decided that we would split our continuity equations into two parts. One part that would treat the chemistry, and so we would look at how to treat the chemistry. And then a second part that would treat the transport, the advection. In fact, we'll add a third part, which is to treat everything else, the small-scale processes, but also then the exchanges, for example, with the surface. Then we started to think about how to treat the chemistry. And here we have a number of chemical species, typically 100, 200. So we have 100 or 200 chemical equations to solve. These equations are coupled because one species influences another species. So in the equation, they are coupled. They're also non-linear. I'll give you an example. If you have a reaction between carbon monoxide, CO, and OH, the hydroxyl radical, clearly CO will be depending on OH, but OH will be depending on CO. So when I write the term CO times OH, which appears as a loss process, it's in fact a nonlinear term because OH is not fixed. It's depending on CO, and CO is depending on OH. So it's a nonlinear equation. Now I have 100 of them that are coupled. And so we have been looking at different ways by which we could solve them. And in fact, we should be at this point a bit pessimistic and unhappy because we see that either we worked explicitly or implicitly. Explicit has a strong limitation on the time step because otherwise the equation is unstable. So that's not good because as we run this long, comprehensive scheme, we have to use such small time step that is really impractical. It's not going to go. It's going to be too expensive. Maybe we can do it in a 0D model because it's one point that we have to solve. But if we start working on a three-dimensional global model with maybe 1 million of grid points, we have to solve this system at each time step 1 million times. Has to be fast. We cannot use small time step. So let's forget about the explicit. Explicit is giving us a lot of trouble for numerical stability, and always one day, for some reason, it will blow up somewhere in the model. So we don't like it. So let's go implicit. Implicit is always stable. It's stable, unconditionally stable, at least for linear equation. If it's nonlinear, maybe it could become unstable for other reasons. So it's much better. But it has a trouble too. Now I have to solve an equation that's implicit, so the solution is complicated. And I showed you that very often I have to invert a matrix, which is the Jacobian matrix. And inverting a matrix, especially if it's a 100 over 100 matrix, takes a lot of time also. In fact, I forgot, it depends on the method, but it could be proportional to n cubed or to n squared, depending on the method. So the bigger the matrix is, very, very quickly the system becomes expensive. So what should I do about it? None of these methods is satisfactory. The first one blows up, the second one doesn't, but it's also very expensive. So we need bright people now to find a way to go around this. And so we're going to look at some method that could help us. Let's think, I told you explicit is not really something we want, but maybe there are some ways of finding other explicit method that will help us. Let's assume, for example, that our equation that we have to solve, or at least our system of equation, is written the way it is here. So I write it in a quasi-linear term. You see the production. So this is the source term. I put a production, I put a loss term, times the concentration of the species here. So I have linearized my equation to a certain way. And so this is against the system. So let's assume one of the equation in the system. If this is linear, if L, which is the, you see P, K, L, K are the K element or component of the vector P and L, well, let's assume they're constant with time. In that case, I can solve this equation over a time step, and here's the solution. It's a quasi-analytic solution, assuming that P and L are constant. It's purely explicit. I don't have to invert any matrix. It's there. It's almost the true the solution if P and L are constant. Well, I can assume first that they are nearly constant, and then I solve this exactly. Now, if the equation is not linear, then, of course, P and L will be depending on the solution, but I can neglect that for a while and then do an iteration. Once I have calculated my new solution, I can recalculate the P and the L value for this new solution, and I iterate. And now I have a system here that is simple, that is almost quasi the true solution. It will be if P and L are constant. It's not exactly if P and L are variable, but over time step they might not change that much. And so I'm going to use this, and I'm going to do iteration if the equations are nonlinear. So I found a way to use a system that is, this is stable, this is analytic, this is stable. It's explicit, easy to solve. I have been able to resolve my dilemma that I had, that I explained to you. Okay, did I succeed completely? No, really no, because this has some problems. First of all, it doesn't really conserve mass. You can show that. It's not mass conserving, contrary to the other schemes that I showed you. So I could lose mass or gain mass as I integrate. So that's not too good. But the other thing is the numerical people will tell you the big disadvantage of this equation is that it has an exponential. An exponential takes time to calculate on a computer. It takes time. If you do it once, it's okay. But now I'm going to do it 100 times. I have to calculate 2 times. 100 times, each grid point, each time step. This method is somewhat slow. So it's slow. It doesn't conserve mass. So it's not perfect. In fact, what people will do very often, and that's done in many models, they will use kind of a hybrid technique. What they say is the following. I'd say for long-lived species, like methane or N2O or the CFCs, I can use the full explicit method. That works. If the lifetime is very, very short, on the other hand, then I assume that I am immediately in photochemical equilibrium, that I have reached equilibrium within the time step, and I calculate the solution as the ratio between production and loss. And then I only use this exponential for chemical compounds whose lifetime is between 1/10 of the delta T and 100 times of the delta T. So this is the so-called quasi-steady state approximation. It is used in many regional models in particular, and it helps using something that doesn't have the disagreement of this implicit method where I have to invert matrices. I don't have to invert anything. It is usually very stable, and it has the disadvantage that I have now to categorize my species between 3 types: the fast reacting species, the long reacting species, and the medium in the middle. The big difficulty with that is that chemical compounds might be long-lived in one part of the atmosphere and short-lived in another part of the atmosphere. So my scheme has to adjust, be different at different altitude in different part of the atmosphere. It works, but it's not perfect. It's not really universal to use. So some people prefer, nevertheless, to use this Euler backward method, which is the pure implicit method. And so what you do here, you solve, you see the equation here. This is the equation, implicit, and then you find a solution. How do you find a solution? You can do it, in fact, without inverting a matrix, and you do it by iteration. In fact, what you do, and we will look at that maybe in the working group, you use what is called a solution obtained by the Newton-Raphson iteration method. In this case, this function here, which is basically the same as here but equals 0, you do an iteration, you develop in Taylor series, and you get an equation like this. And you do then, of course, you have to invert your Jacobian, but you can do something interesting there when you have a Jacobian to invert. In fact, when you look at your system, you might have a big system, let's say, of 100 by 100 chemicals. So you have a big Jacobian, 100 by 100. Look at this Jacobian. Look at the matrix. Many of the elements are 0. The matrix is called a spare matrix, sparse matrix. A lot of the elements are 0. Why? What are the elements? The elements are essentially the sensitivity, the derivative of the source term to the chemical species. So you will have only a non-zero term between two species if there is a reaction between them. Not all the species react with all the species. Many species, like for example, methane does not react with SO2. So the element of methane and SO2 will be 0. In fact, a Jacobian has perhaps 30% or less, 10% sometimes, of the elements in the matrix that are not 0. Everything else is 0. And so the techniques to invert spare matrices, and I'm not going to go into the detail, but so you can use that to accelerate your inversion of the matrix. There are other methods. I'm not going to describe that in detail, but you might have heard about them. For example, the Rosenbrock method, which is shown here. It's a kind of an extension of the so-called Runge-Kutta method. Basically, you write that the solution at n plus 1 is the solution at n plus a term here, delta t, times a number of elements, and these elements are here, and then again you have to solve them. These Rosenbrock methods are very accurate. They're a bit slow, but they're used now more and more in chemical model. This is an example of one of them. We're not going to describe them. I left those view graphs so that when you get them, you can look at those. That's the Rodas tree. It's a bit more complicated. You write the solution at n plus 1 is the solution at n plus a number of terms that are here. And in fact, you have to solve this system for K1, K2, K3, K4. See, K1 depends on K1, so it's implicit in a way. And so you have to solve that. And again, there are standard methods to do that. A method that has been used a lot, that you might have heard about, is the gear method. This method is what's called a multi-level method. In other words, what you say here is that your solution at n plus 1 depends on the solution not only at n, at the previous time step, but it depends on the solution of the previous from the previous, the previous from the previous, from the previous. You can say it depends from the solution at many times before. And you can take k, which is here, to be 0, to be 1, to be 2. And then you have the term here for the source. And again, you calculate the source at different previous time step. All the methods I showed you before were saying the new value depends on the previous value. But you can also make it dependent on the previous value, the previous value, the previous value. Before that, it increases your stability. It increases your accuracy. And one of them is the gear algorithm that is shown here. And this value of k, you can change it in fact, then you put that into your equations, you find something like that, and it's an implicit method. You solve it with an iterative approach, and in the usual gear method that you find on the internet, for example, you will have an automatic adjustment of the order of the method. That's this value of k here, and the time step. They will adjust themselves automatically to be as accurate as possible and stable. So these methods are very robust. If you run something that has a big discontinuity, for example, between daytime and nighttime, concentration goes down. The usual method will fail when you transit from daytime to nighttime because of these fast, abrupt changes in the concentration. This method will not fail. What it will do, it will say, okay, now I'm in the middle of the night, nothing changes. It will take automatically big time steps and a low order of the method. K will be low. Then suddenly it comes to the transition where the sun shows up and all the concentration change in your system. It will first go on with the large time step and the low order of the method, and it will fail. And then you say, stop, I failed, I go back, and I start with a time step 10 times smaller. I increase my order of the method, this value of k here, and I start again. Maybe I fail again. I do a second reduction of my time step until I don't fail anymore. And then I'm back in the daytime where things are relatively no transition. I will re-increase my time step and so on. So it's a very automatic method that is very robust, very accurate, and is used very often as the reference. The trouble is that it's implicit, it's therefore expensive, and you cannot use the gear method in a three-dimensional model. It's just too expensive at the moment unless we get faster computers. Okay, we have not talked at all about chemistry because Paul Monks was there, and I'm sure that he put you a few equations on the board yesterday. And so I said, well, now that we have seen a bit what the numerical method is, let's go and explain a bit how we would use it. Well, this is an example here of a tropospheric chemistry mechanism. It's a very simple one. I think there are like 10 reactions. It shows basically how ozone is produced. You see here, for example, the photolysis of ozone that produce OH. Produce first, of course, O single D that then reacts with water, produce OH. OH will destroy a hydrocarbon and leads at the end to the formation of ozone, for example. And in fact, you see here our ozone, OX, which is basically the total of these, and arrow X and OX change. This is what I would call a one-slide mechanism, a simple scheme. And if we wanted to solve this one, we would have to solve it for probably about 10 equations, a very simple scheme. Of course, in reality, we have more complicated schemes. And typical 3D model for air quality use, as I told you, 100 to 200 reactions. So our Jacobian will be a matrix of 100 over 100 or 200 over 200. If we go in box model, 0D model, we can put much more complicated schemes. We only have 1 point to deal, not a million of pounds like in the global model. And so usually these models might include 5,000 to 10,000 reactions. The trouble is that we don't know very often the rate constant for all these 10,000 reactions because they have not been measured. So we have to guess them or make a judgment on them. There are now also models, some developed in France here, where they generate the reaction. So you don't prescribe a list of chemical reaction. They just take all the species that they can think of, and they react them with all the species that you can think of. So you take, whatever molecules you have, you make them react. You don't know, of course, very often the rate constant, but there are rules by which you can guess them. And so there are few models, one in the UK, one in France, that now treat 1 million to 10 million chemical reaction and have to solve at each time step this chemical scheme using one of the techniques that I showed you. Let me give you an example to show you how complicated things can be. We're going to take one hydrocarbon. I think this is pentane. Yeah. And pentane is here. We don't even write the formula anymore, but the structure of this organic molecule. And you see what happens in this scheme going down, this degradation happens. And you see that as this happens, there are radical sinks, shown here by the red arrows. There are conversion between NO and NO2, which is a source of ozone in the troposphere in general. So you have to take all that into account. It becomes, of course, very often, very quickly complicated. So there are a number of attempts that have been made to say if you deal with, say, air pollution, let's say ozone, I'm not talking about aerosols at this point, you have different attempts to reduce the number of chemicals to have a scheme that makes sense, that brings you relatively good, accurate results without having to take into account 1,000, 2,000, 3,000 reactions. So you have the so-called heuristic scheme here, like the one-slide mechanism that I showed you. You can go to all textbook. They will show you some scheme that more or less with maybe 10, 20 reaction explain, say, the ozone budget in the troposphere, more or less. You have then more complex schemes that lump a number of chemicals. How many hydrocarbons are released? Many, many of them. And they all degraded, like pentane. Many, many, many reactions for the degradation of each of them. You cannot treat that realistically in an air quality model. But what you can say, well, I'm going to take pentane, butane, and so on, and I'm going to lump them into one hydrocarbon. And I'm going to assume that this one hydrocarbon that in fact accounts for many of them is degraded according to, let's say, pentane. So I'm going to treat one of them, but in fact, it's not pentane. It's pentane and many others lumped together. So some people do that. You see here a number of these mechanisms, the CB4 mechanism, the radar mechanism. These are example, the Sparks 99 mechanisms that are here. Finally, you have the more explicit scheme, the NCAR master mechanism, the Leeds master mechanism. I know that Paul Monks is probably advocating for the Leeds mechanism. I will, of course, advocate for the NCAR mechanism. But then Bernard Aumont in France has developed this self-generating mechanism that has a few million chemical species. So you can go from very simple one-slide mechanism that I showed you to a much more complicated story. So far for the chemistry. I think we have seen that, of course, we had difficulties with this explicit implicit method, but that we had ways to go around using clever approach, if possible to use some explicit approach that are easy to use, or to find ways by which we can invert our implicit system in a way that is not too slow. Personally, I like most the implicit method with a clever way to treat my Jacobian inversion, because at least I know that it is robust and stable. And frankly, when you put it in 1 million grid point, there is, if you use explicit method, there is always a point where suddenly it blows up. You don't have that so much in the implicit. Now, implicit is unconditionally stable when the equation is linear. But of course, when you have nonlinear equation, when you put a lot of species together, this kind of easiness of the stability that I described might fail also, so that in practice, you will have always to limit your time step, and otherwise you will be in trouble. Okay, so far for the chemistry. We're now going to go to another component, and that's the transport, and in particular the advection. In fact, if you look at the equation that I showed you at the beginning, I said we have to distinguish between the transport that we can resolve, the one that our model will see and be able to simulate, and then the transport that occurs because of very small scale movement in the atmosphere that occur at a size smaller than the grid, and this one the model cannot reproduce them. Nevertheless, they are important, they play a role, so I have somehow to take them into account. We're not going to talk too much about unresolved processes. Very often we will simulate them, parameterize them, using a mixing approach. We will assume that when you have turbulence, you just mix the species. And so mixing is like diffusion. And so we'll treat diffusion. Maybe we'll talk about that in the working groups. We will focus on advection because the problem, I think, is interesting. But before we do that, we should remember that the time scale associated with displacement of molecule is very different from different parts of the atmosphere. So if you want to bring an air parcels from, let's say, the US to Japan, it will take you about 2 weeks. If you want to bring it from the US to Canada, it will take you about 2 months. The transport, the longitudinal transport is much faster than the latitudinal transport. And of course, if you want to cross the equator, it will take you at least a year. You see that, of course, that has implication on the way pollutant will disperse and be transported in the atmosphere. If I look at vertical exchanges, first of all, inside the boundary layer of the atmosphere, it'll take you about 1 or 2 days to mix. To get out of the boundary layer and get into the free troposphere, it will take about a week to go. To mix into the whole troposphere, it will take about a month. And if you want to go into the troposphere, the stratosphere, from the troposphere to the stratosphere, it will take years. It's very, very slow process. And of course, that should be reproduced by your transport model and your simulation that you will do. So, as I mentioned, we have resolve, advection, and we have perhaps mixing that we will represent by diffusion term. And you see here, again, with a you see here an equation that is a bit simplified, that has basically a wind speed, c, that I will assume to be constant in all my presentation, and you have an eddy diffusion, k, that is shown here. Advection operates with a first order derivative, diffusion operates with a second order derivative. So I'm going to take a signal, rho, at the initial stage, which is a square. And of course, if it was just advection, and the wind c goes to the right, what would happen to this signal, to this function, to the square function? It would be translated to the right at a speed that is equal to c meter per second. So in fact, in the case here of the one-dimensional equation, with a constant velocity c, I know exactly what the solution is. I have to take my initial condition, which is a square here, and I have to translate it in the direction of the wind speed. So it is, in fact, a very easy problem to solve analytically. I know my solution very well. If I add, on the contrary, now diffusion, what is the diffusion going to do? It's going to let my square diffuse and to spread, and that's, I will assume it's due to small turbulent motion that will spread my initial square function. And so what you see here as the two together, first of all, you see the translation with the advection here times t1. It has been displaced by c t1. and you see that the shape of my signal has changed due to the diffusion, and the diffusion goes on, and the species will spread more and more. Well, we're not going to talk about the diffusion part. Now we're going to talk essentially about the advection part. And so let's see how we will solve this. First of all, we should remember what the continuity equation is. And in fact, I'm going to write it here. You remember this equation. Of course, when chemistry was included, the 0 here was replaced by a source term, Si, or S. Now, I will remove S because I forget about chemistry. I assume chemistry is not operating. I assume, therefore, that all my tracers are inert. They don't undergo chemical transformation. They are just transported. And I'm going to look at numerical techniques to solve the advection equation. So this is the advection equation in the flux form or the Eulerian form. I can introduce the mixing ratio, as I showed you yesterday. In this case, the equation becomes here in the advective form. Mu is the mixing ratio. V, like here, is the wind. By the way, the product here, rho times the wind, is the flux, which I will note F. Then coming back here to the advection form, this total here is equivalent to the total derivative. And I find again what I explained yesterday. We have conservation of the mixing ratio along the flow, and so I will use that as my Lagrangian form of the continuity equation. Continuity equation, again, that is neglecting or omitting, ignoring chemistry. So I need to solve this. By the way, there are integral forms of the equation. If I have a kind of a complicated grid, like the one shown here, this is an hexagonal grid, and I showed you today we start using hexagonal grids or icosahedral grid. In this case, I like to integrate over a volume, if it's a volume, or an area, if it's a two-dimensional grid. I integrate my continuity equation, and I like to do that because basically what I say by doing that is that the mass of chemicals is a conserved quantity. I can then apply this. There are some theorems, like the Gauss theorem, that shows that at the end, the change in the mean concentration inside this complicated grid cell is in fact proportional to the flux that, the change in the concentration is proportional to the flux that enters into the grid and goes out of the grid. You can, of course, understand that if I have a volume that can be very complicated. Here it's beautiful, it's hexagonal, but it could be any grid. The change in the concentration, in the mass inside the grid, depends on how much mass goes in minus how much mass goes out. And we will use that quite a bit. If it's a one-dimensional approach, because we will only talk about one-dimensional approach, the mean concentration in a grid is basically controlled by the difference between the flux that enters on the left and the flux that goes out on the right if the wind is positive. So we have these equations. Of course, I told you in a simple case, we can solve them analytically, and we know the exact solution. It is displaced to the right at the speed of the wind velocity. But of course, that's a simple case. First of all, the wind is not constant, so that will change. Number two, the problem is not one-dimensional. We have winds that are very complicated in the atmosphere. And so if we start with any function that we want to advect, it will not just be a translation. It will be much more complicated. And then we have no analytic solution. We'll have to look at a numerical solution. So what do I want my numerical solution to accomplish? I have requirement when I go to the mathematicians. I say, don't give me anything that I cannot live with. I want a number of things. First of all, I want an accurate solution. It has to be accurate because transport is complicated, and I have to be close to the true solution. Number two, I want my method to be stable. I don't want it to blow up. And so the solution should not diverge. I want what's called monotonicity. If I have a function that I transport, I don't want my method to create peaks, minimum, undershoots, overshoots that are purely artificially produced by the numerical techniques. Why? Why am I so nervous about overshoot and undershoots? Well, overshoot is okay maybe, but undershoot, it could make my concentration to become negative if it's a very deep undershoot. And I don't want a negative concentration, because if the concentration in my model of ozone becomes negative, and I want ozone to react with OH, I mean, the reaction between a negative species and a positive species gives me something strange, and my model will blow up. I want conservation of mass. I don't want my advection scheme to create mass. That would be a bit strange, or destroy mass. I want the transportivity conditions. You can understand that. If the wind blows from this direction and you emit something here, it has to go in this direction. I don't want the compounds to go in the direction that is upwind. It has to go downwind. So that's very important. Some models, you will see, create material upwind. I want locality. I don't want, if I emit something in the South Pole, I don't want 10 minutes later to be here over Bayonne or Biarritz, because just of a numerical artifact. Needs time to come. So I want correlativity. If I have correlations between species that exist, my method needs to preserve that. I want flexibility. It would be good if my method could be applied to different grids, different resolution, so that it's very general. And then I want efficiency. My computer costs me a lot of money. It has to be fast, especially the faster it is, the more resolution I will gain in my model. A lot of requirement. Does anybody know a method that fulfill all these requirements? If so, you can continue the lecture, because I don't know any of them, and you will see that there are limitations. Okay, let's go to the one-dimensional advection equation, and let's see what we can do with it. I'm going to write this equation like this. Whoops. It is here. This is the equation. C is the velocity. Phi is the function that I will advect. Usually it's a concentration, but it could be something else. I'm going to assume that there is an initial distribution. So the function C at times 0 has a given function distribution that I'm going to supply. I'm also going to say that as things move, I need to know what's coming. You know, if I have a certain area that I'm considering and the wind moves this way, I need to know, of course, what's coming from outside. I need boundary conditions. The boundary condition is now, in this case, the concentration at x equals 0 and varies with time. And this is also prescribed. Of course, you see that, in fact, to be well posed, you should only have a boundary condition upwind, upstream, and you cannot fix the condition downstream, because you don't know what it is. And then the analytic solution, as I said, is a pure translation of the signal. And I write it this way. I take the initial signal, x, and at times t, it's just the same signal translated by c t over a time step c delta t. Here's an example. You take, this is, say, the initial condition here, and you assume that it remains constant at x equals 0, and then it is translated. The velocity here is constant. So that's the solution. Now I will try to simulate that by numerical technique and see if I can do it. Well, remember what the equation is. It has a first-order derivative in time and a first-order derivative in space. So I will have to discretize my equation and again see how I'm going to calculate in particular the derivative in space. Well, here is one way. I'm going first to assume space center differences. What does it mean? It means that I take here the derivative by doing the finite difference, looking at the value at j plus 1 minus the value at j minus 1 divided by 2 delta x. So if I look at the derivative at location j, I take the derivative by the difference from the value in front of me minus the difference in back of me. I put that in the equation. This is now the time derivative, one level, n plus 1 minus L at points j, and I calculate the derivative here as shown here. I can then calculate the value at times n plus 1 at location j as a function of the value at times n location j plus this. Alpha is c delta t over delta x. And in fact, what I can show you, I don't do it now, this method is unconditionally unstable. It will blow up whatever time step or whatever value of alpha here I am taking. So this simple center method is unstable. And there are ways by which I can stabilize it. First of all, what I can do, I can say, well, I'm going to add a bit of diffusion, because if it's unstable, I'm probably putting a lot of wiggles, and if I can smooth them, then I might stabilize my equation. In fact, what you see, you will add a term, a diffusion term of your equation, you discretize it like this, then rather than having the first term here, as in the previous equation, you add a certain term here, which is a diffusive term, and diffusion usually stabilize your equation. A lot of people add artificial diffusion in their advection scheme to keep it quiet and stable. This is what we're doing here. And then, of course, there are stability conditions that are shown here, but we might have stabilized it. That's one way. Now, there are methods that I will just show you one of them that have been introduced to stabilize things. For example, Lax. Lax method, basically, in this equation here, he replaced the terms, this term here that appears in the first term here. You know, if you go back, let me go back for a second. You see this equation here. He basically took this term here, phi at points j. He said, well, I'm going to replace it by half the term at j plus 1 and j minus 1. If I do that, I become this. And what you can see, it looks like the equation that was blowing up, the unstable equation, plus a term that has the characteristic of a diffusion term. In fact, it is equivalent, basically, of solving not just the advection equation, but adding a term like this that has a kind of diffusion coefficient that is equal to delta x squared over 2 delta t. And this method is stable if alpha, which is called the CFL coefficient, is less than 1. So basically, there are ways by which you can improve the center difference and you can make it stable. This is another one here. In this case, you keep the center difference, so that would normally be unstable, but you change the way you calculate your derivative. You take now what's called a leapfrog technique. So rather than calculating t minus delta t, or n, or let's say n plus 1 minus n, you calculate n plus 1 minus n minus 1 over 2 delta t. So it's centered not only in space, but also in time. This is then explicit. It's conditionally stable also if your CFL, so-called CFL criteria, is fulfilled, is c delta t over delta x is less than 1. Now, this is a criteria, this unconditionally stable criteria. You will find that in many methods, in many advective methods, and it's a pain. Because basically what it does, it limits your time step delta t. If you have a very small delta x, a very high resolution model, very small delta x, your delta t will have to be equally small. So if I increase my resolution by a factor of 2, I have to decrease my time stamp by a factor of 2. So not only do I have more grid points to deal with, which costs me time on the computer, I will have to reduce my time by 2. So basically, doubling the resolution is a factor of 4, 2 times for delta x, more grid points, but the time step 2 times smaller. In particular, near the pole, where all my meridians are coming together, I will have a very small delta x there near the pole. I can only, and that's for the global model, so I can only use a very, very small time step there. And so all these Eulerian methods that I'm showing you are a bit of a pain from that point of view. That's another method. That's an implicit leapfrog. And this one is unconditionally stable. So basically what you do, you take the leapfrog here. So you center the difference in time, and you take half of the value in space, implicit and explicit, and it's difficult to resolve, so we don't like that either. So center method, you will see have other problems. I will come to those in a second. But I'm going to go now to the space uncentered difference. In fact, it makes more sense to use an uncentered method. What you do here, you approximate your derivative in space by the value at j and the value upwind at j minus 1. Why does it make sense? Because basically, the solution here depends on where the material is coming from, upwind, upstream, as we say, and doesn't have to depend at all of the solution that you see downwind. The center difference was making the difference between an upwind and a downwind value. And the value downwind, I don't know. It's unknown, in fact. So here what I say is that my value here depends only on the upwind, where the material is coming from. So it is uncentered, and then you can basically replace your equation by this one if the wind is positive or if the wind is negative. So you have to, if the wind is coming from this way, upwind is this point. The wind is now coming from this way, upwind is on the other direction. So it's more complicated to deal with. It has big advantage. The solution is it's always positive, but it's very diffusive. In fact, you can see here a signal that I'm going to move to the right, and in fact, the signal after a while has this shape. I have not preserved really my shape. I have diffused my shape. It is stable again if this criteria is realized. So the method assumes that the value of the function at point j is affected only by the value at the upwind point j minus 1. And again, it is positive, no negative concentration, but diffusive. And of course, I'm not sure you would be happy if I told you that a plume moves like this and becomes this, when in fact there is no diffusion prescribed in my model. It's purely numerical diffusion. I hate to see numerical diffusion, but it has good sides. I don't get wiggles. It's stable for some criteria. The leapfrog, for example, just to show you, here's the leapfrog. You see my signal? What it does, after a while, it starts to get negative concentration. It creates wiggles upwind. I don't like that at all. It's only stable if this criteria is there. So, which method from the two would you like to prefer? The one that's diffusive or the one that is not diffusive? It's called dispersive and create wiggles. Not all the frequency in a signal are transported at the same speed. So here's a list of many methods that exist. We talked about the earlier forward. I told you always unstable. We talked about the lux that is stable for this alpha less than 1. We talked about leapfrog. There are many others, and you can see that they all have, most of them have a criteria. Some might be stable or unstable. Some are dispersive, dissipative. So they all have advantages and disadvantages. Well, here is a test that we did. We took this square function. This is the lux method. You see that it's not too bad, but it's slightly diffusive. The earlier forward is completely unstable. The leapfrog, well, it's not really perfect. Then we have other methods that are a bit better, but nothing is see this one, for example, create negative concentration, Lax-Wendroff. So we hate that as chemists. Then we have the upstream, the Matsuno method, but see, you might have some problem. Nothing really is perfect. And they all have, if they are stable, most of them at least, this criteria alpha less than 1, which restricts my time step really considerably. How much time do I have?
5 minutes.
5 minutes. Okay, just go quickly and conclude this. Center methods are not positive definite and characterized by noise. You see that. Earlier forward is unstable. Other algorithms can be stable if alpha is less than 1, but are not free of oscillation. Uncenter method called upstream or upwind are free of oscillation, thus positive definite, but are diffusive. And usually you have to follow also this alpha minus 1. So basically, none of these two are very good. Just like in the chemistry. We have two ways of approaching the problem, and nothing really works well for us. So what we will have to do is find other methods, better methods, higher order methods, as I will show you, that are addressing some of these problems. In fact, we are going to forget the center method, essentially. We're going to go in the uncenter method, the one that are diffusive, and we're going to try to reduce the diffusion. If we can do that, we reduce the diffusion. We know it's positive definite. It has a lot of advantage, and so that's what we're going to do. So basically what people try to do, maybe I should go here, is to, you see the different cells here, delta x, so 1, 2, 3 cells. Usually what we do, we take the value in the cell, and we transport the value in the cell. We'll do that again, and I'll show you what it does. It's diffusive. So we can do probably a bit better, and we can assume that inside the cell, if we have a function, it's not really constant, but it might vary linearly, so that the average is the point that is shown here. And then we can move not only the value of the function, but also the slope of the function. Then it will be less diffusive. And if I want to do a bit more, I will not assume it's linear, but it's quadratic, more or less. You see it. And I will move the function, the first derivative, which is the slope, and the second derivative, which is the curvature. And if I can do that, I will be even less diffusive. So let's see here, for example, this is the first case on the left where we have this here, and we're going to basically say that the function at a given cell, so now we're looking at the cell, is equal to the function in the cell at times n times the flux that's coming in minus the flux that's going out. So basically here is a design. If we run over delta t and see all this material in gray will move from this cell here into the next cell. This one will move into the next cell, and so on. So that my flux that's coming, say, through here, so flux j minus 1, is in fact the integral of the function over this, basically the integral here under the gray area, which is shown here, from x minus j minus half to this value here, xj minus r minus c delta t. So this is the material, the flux times delta t, the flux that enters over a period delta t. So I replace this, and then I find basically this relation here, which is basically giving you my function in the cell j at times n plus 1 equal the function at times n plus basically this term. By the way, you will see that this is exactly the same relation as the one we had in the original upwind or upstream method. So it is diffusive, and as I said, we have to do a bit more. Well, Michael Prater said basically what I said a minute ago. He said, rather than assuming that the function is constant in the cell, I'm going to assume that it's a quadratic function. And what he did essentially, he says during it, so he writes, you see here the function as a quadratic function, ax squared, by, this is in 2 dimensions. And so over time steady delta t, he used the upstream method, the one that's diffusive, but he doesn't only move the mean value called a0, he moved the whole thing here, the derivative, the slope, the curvature, and this method is then very, very little diffusive. Let me just tell you about another method if I have 5 more minutes. No? Okay, 2 minutes. Lagrangian approach. Basically what you do, you take air parcels and you transport all these parcels along their trajectory, and you can do that. You can take a long time step. There is no criteria of stability. And we will discuss this then in the afternoon. You can use semi-Lagrangian method, which basically says that if you have a grid, like in the Eulerian model, the value at this point here, if the mixing ratio is conserved, is basically the value at a previous time step where it used to be located. And so you do essentially a Lagrangian calculation, but you kind of put things back on the different grid points at every time step. And this is what we're going to discuss in the afternoon. You can see that essentially what we have done, we have used the original simple fundamental method. We have seen that some have a lot of noise, especially the centered method. So we're going to abandon them. We took the uncentered method, the one that basically our upstream method takes the information from upstream from where we are. We saw that this method is diffusive, but we can correct for that by introducing higher order method where we don't only move the material, but we move the shape of the distribution of the material by moving the first derivative, the second derivative. So we have higher order method. These are still Eulerian method. The Prater scheme is an example. There are others. They still are bounded by the CFL, the alpha less than 1. So they don't really work very well for global models because of the pole problem. So we move into more Lagrangian approaches. Lagrangian approaches is really to look, you take 100,000 parcels and you see where they move. It has some difficulty, which we can discuss in the afternoon. And so we take a compromise between Lagrangian and Eulerian. We take the semi-Lagrangian method, and if you come to my discussion in the afternoon, we'll move into the semi-Lagrangian technique, which is used really by a lot of models today. It has also disadvantages. It does not conserve mass unless you take some precautions. So, thank you very much for this, and I hope you got something out of all that.